Infinity is a strange thing. It has puzzled and entranced many mathematicians and angered a significant number of non-mathematicians. But when we truly take the time to analyze and examine it, it can actually be something very beautiful. How beautiful? Well, who cares how beautiful? Either something is beautiful or it isn't. While my entire audience is furiously arguing with me right now about what I just said, the point I'm trying to make is that the attitude with which I just said that sentence is the same nonchalant attitude with which the majority of people approach the concept of infinity. First off, infinity isn't a number, it's the size of a set. Infinity is not the last number on the number line, it's how many numbers are on the number line. But like the analogy I made to a scale of beauty, there are different sizes of infinity. The smallest size of infinity is countable infinity. We call it countable because although there is no end to the number of elements in it, we can count and transition from one element to the next. The set of countable infinity is the set of natural numbers, so 1, 2, 3, and so on. It's also the set of all integers, the set of just even numbers, and the set of just odd numbers. Now this might be hard to believe, but it is provable using an argument made by Cantor, a mathematician who is considered to be the father of set theory.
Let's say I wanted to play this chord. It would be played like this. Now how do I know that I'm pressing the same number of keys as I have the number of fingers in my hand? Well, I could count the number of keys I just pressed. 1, 2, 3, 4, 5. And, well, I have 5 fingers, so that counts. But the way pianists usually tell is because there is a one-to-one match between the keys and the fingers. Since each finger is paired with a key, we can tell that both sets, the number of keys and the number of fingers, have the same number of elements. And this is basically what we're doing with the countably infinite set.
So I can use that same argument, and what I can do is I can take every natural number, 1, 2, 3, 4, 5, and so on, and I can pair up every natural number with an even number. I can pair up 1 with 2, 2 with 4, 3 with 6, and so on. Since I won't run out of either natural numbers or even numbers, there is a one-to-one correspondence between each, and thus we can say that the countably infinite set of natural numbers is also the same set of just even numbers. Now we can use a similar argument to show that a countably infinite set also contains all rational numbers, which might seem counterintuitive, but it is provable by the same argument. What we can do is construct a table with just rational numbers, and using Cantor's argument, we can make a one-to-one correspondence with each rational number and match each rational number to a natural number. And this argument will always hold. A good way to see how countable infinity is dealt with is with Hilbert's paradox of the Grand Hotel. Imagine a hotel with an infinite number of rooms, with a countably infinite number of rooms. Now imagine that in every room there is a guest. Supposedly the hotel is full, but it isn't, because if I walked in and I asked for a room, I won't have to be turned away. All the hotel has to do is move the guest in room 1 to room 2, the guest in room 2 to room 3, 3 to 4, 4 to 5, and so on. So each guest in room n is moved to room n plus 1, and still every guest has a room, and room 1 is free for me. This works with any number. Let's say that 3 people come in and ask for a room. All the hotel has to do is move every guest in room n to room n plus 3, so 1 to 4, 2 to 5, 3 to 6, and so on, which leaves the first 3 rooms open. It doesn't even matter if there's a bus full of a countably infinite number of people. We can just move every guest in room n to room 2n. So guest in room 1 would move to room 2, 2 to 4, 3 to 6, 4 to 8, and so on. Now every even number would be booked and every odd number would be empty for the incoming guests. They're too big to count. These are the uncountably infinite set is the set of all real numbers. And we call it uncountable because we can't even count from one element to the next. I mean, for example, let's try that. So let's say I start at 0. What comes next? Would it be 0.0000000? There's got to be a 1 at the end, right? But there can't be. I can always put another 0 before the 1. So this just demonstrates how big uncountable infinity is. But let's prove that it's bigger than the countably infinite set with Georg-Cantor's diagonal argument. Now imagine, for sake of simplicity, I just listed irrational numbers between 0 and 1. Imagine I listed a countably infinite set of these decimals. Now what I can do is I can pair each decimal with a natural number. And this will go on forever. Now, if there is a one-to-one correspondence between the irrationals and the naturals, then we will know that they are in the same set. But we can still generate more real numbers. All I have to do is take the diagonals in every row. So I'm going to take the first decimal in the first row, and I'm going to add 1. Then I'm going to take the second decimal in the second row and add 1 again. I can keep doing this, adding 1. I will subtract 1 if it's a 9, but what I'm essentially doing is I'm going to take these values and I'm going to create a new decimal, which will be different from every decimal on this list. And since this is not paired with any natural number, since we've used up all of them, there are still new real numbers that can be generated from this. But let's swim in waters a bit deeper. The countably infinite set is denoted by aleph null, which is the first smallest infinite cardinal. Now a cardinal is any rational number. 20 is a cardinal, 100 is a cardinal, and the cardinality of a set is the number of elements in a set. So the cardinality of this set is 20, and the cardinality of this set is 5. But now let's ask, what comes after all the naturals? Since we've used up all of them, let's say we want to put another one. What do we put for this element? Well, after we've used up all the cardinals, we need transfinite ordinals. And the first transfinite ordinal is omega. After omega comes omega plus 1, then omega plus 2, omega plus 3, and so on. Now keep in mind, these ordinals are still in aleph null. I can demonstrate this by simply relabeling all these elements. I can label them 0, 1, 2, 3, 4, 5, and so on. So in that sense, the ordinals aren't bigger than the cardinals. They just come after the cardinals. So now what we can do is just run past these ordinals until we reach omega plus omega, which is omega times 2. We can then go up to omega times 3, omega times 4. What about omega times omega, omega squared? What about omega to the omega? So, and the best part is these are all still in aleph null. So what if we try to go past aleph null? Well, after we go past all these ordinals, past aleph null, we get to the next smallest infinite cardinal, which is aleph 1. And the corresponding first transfinite ordinal is omega 1. Now we can keep scaling this up to different infinities, so we can have aleph 2, aleph 3, aleph 4, and we can just run longest, even up to aleph omega. But let's go back a few steps because we left something behind. Where does the uncountably infinite set fall in this number line, the set of all reals? somewhere in Aleph Null. It could also be larger, but it could, as the famed Continuum Hypothesis states, be equal to Aleph 1. The Continuum Hypothesis is the greatest unsolved mystery in mathematics, and to this day mathematicians can't either prove or disprove it. It states that the set of all real numbers, which is denoted by a fractor c, is equal to Aleph 1, the second smallest infinity. In the early 1900s, Ernst Zermelo and Abraham Frankel formed the Zermelo-Frankel axiom set theory with choice, or ZFC, and it was designed with theorems and axioms concerning infinity, and it meant to get rid of all paradoxes in set theory, such as Russell's paradox. But try as they might, they could not fit the continuum hypothesis to be determined in this axiomatic system. Though the continuum hypothesis was consistent with it, it was not able to be proved true or disproved to be false. Unfortunately, the appeal of the continuum hypothesis was somewhat lost in the 1940s when a certain Kurt Gödel came along and published his famous incompleteness theorems, which I covered in my previous video. What he professed was that mathematics would never be complete, that not everything in mathematics was provable. Though mathematics was turned upside down by this, it still only became more fascinating to mathematicians who are still trying to solve the greatest mysteries in math, like the continuum hypothesis. And who knows, one day maybe they will. Maybe one of you watching this video right now will be the one to solve it. And to that I say, to uncountable infinity and beyond.